Welcome back to our statistics class. Got a new word for today. The new word is or. We've been doing a lot of this probability of A and B, two events happening at the same time, simultaneously, concurrently, whatever word you want to use. We've been looking at probability of A and B for a little while. Well, now we're going to look at the probability of A or B, which means maybe A happens, maybe B happens, or maybe both. We're not worried that it's, A but not B or B but not A. We don't care about that. Just either A or B and we're happy. That kind of or. Turns out there's something called Bayes Theorem, which handles the general case. But before we get to that, let's look at the special case. The easiest situation, you hope that this happens a lot in your life because it's the easier situation, is when you have a special case, something called mutually exclusive events. If you have two events and they are mutually exclusive, what's that mean? It means they cannot happen simultaneously. Like, for example, I'll put like, hey, my thing moved. Why'd you do that? Come back here. Okay, so like a car cannot be both a Jaguar and a Fiat. Sure. A car is going to be a Jaguar, maybe. A car is going to be a Fiat, maybe. You're not going to have a Fiat Jaguar. You're not going to have a Jaguar Fiat. They're two completely different kinds of cars. They don't even make them in the same country, for goodness sakes. Very different. So the probability of selecting a car and it's a Jaguar versus the probability of selecting a car and it's a Fiat, these are an example of what we call mutually exclusive events. For a more mundane example, a card, a playing card, maybe I should say playing card, but a card cannot be both, not with a normal deck anyway, cannot be both a heart and a diamond. It can't be both, right? It's going to be one or the other, or even something else entirely, but it's not going to be both a heart and a diamond. Stuff like that. That's what we mean by mutually exclusive events. And if you have mutually exclusive events, then the rule, so to speak, formula, if you want to call it that, we express it this way. The probability of either event A or event B happening is, all you guys to do is add them up. Just add them up. That's all you got to do. So I'll put that in a big box, and I'll put the special note here, and this is important, so maybe I'll put it in a different color, like this fuchsia thing. This formula, this which says, hey, I can just add them up. That's what the formula says. Assumes that your events A and B are mutually exclusive. If they're not mutually exclusive, you cannot just add them up. So be careful about that. But if they are mutually exclusive, you can just add the probabilities up. So here's an example. You got one card drawn at random from a standard deck of 52. Find the probability. It's either hearts or spades. Well, if you got a full deck and it's all well shuffled and all that, the probability that it's hearts, well, we have an equal number of cards in each suit, and there's 4 suits. So really, the probability that it's hearts is going to be 1 in 4, because you're going to get one of those suits, right? Put the card back. Put the card back. Now, the probability of getting spades, and I hope you don't mind if I draw a spade like that, is about, well, it's the same. It's 1/4, right? Because, again, there's 4 equal suits. Now, the thing is, these are indeed mutually exclusive events, right? Which means if you want to find the probability that it's either a heart or a spade when you draw that card, either a heart or a spade, all you got to do is take that 1/4 chance that it's a heart and the 1/4 chance that it's a spade and add them up. 1/4 plus 1/4 is 2/4, which is a half, and I'll put a check mark next to it. Probability of getting a heart or a spade is 1/2. Mutually exclusive. Add them right up. So whenever you know you have mutually exclusive events, you're going to add them right up. Now here's a somewhat more involved example. We're going to toss 3 fair coins. So these are independent events, right? The coins are independent. Each result has nothing to do with any other result, right? They're all independent to be heads or tails, however they please. Find the probability exactly to our heads. Okay. I think I'll do this problem 2 different ways just for the practice, just for the exercise. First, let's do a tree. We haven't done a tree in a little while, I don't think. So here's Biff. First thing he's going to do is toss one of those there coins, and it's going to come up either heads or tails, right? That's the first flip. Now, if he tosses heads on the first, then it's either going to come up heads or tails. And if he tosses heads twice in a row, then the third coin is either going to come up heads or tails, right? If he comes this way and does a heads and then a tails, well, the third coin will be either a heads or a tails. And hopefully this is looking familiar. Coming down here, if he does a tails first, the next coin will either be heads or tails. If he does tails and then heads, he will then do either heads or tails. If he does two tails in a row, he will then either do heads or tails. So notice we've got, you know, these 8 different paths. Heads, 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 tails, heads, tails, heads, heads, tails, tails, and so on. We've got 8 equally likely outcomes. In fact, let's put that in a different color. 8 equally likely outcomes. All of these are mutually exclusive, right? You're not going to get heads, 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 and at the same time get tails, 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 or at the same time get heads, tails, head. You know, these are all mutually exclusive outcomes, all 8 of them. All are mutually exclusive, which means we're going to be able to add something up. What? Well, let's see. What's it say? Exactly 2 heads. How can we get exactly 2 heads? Here's one way to get exactly 2 heads. Notice I have to go down, not up, because I don't want 3 heads. I want exactly 2 heads. So one way to do it is to get heads, heads, and then tails. And the probability of that is 1 in 8, right? Because these all have 1/8 probability. What's another way to do it? Well, you look around and you say, well, 2 heads, huh? Well, I could go like this, heads, and then tails, and then heads. That works. So that would be heads and then tails and then heads, and the chance of following that path is also 1/8, again, because there's 8 paths you could follow, and they're all equally likely. And then another way you could get exactly 2 heads is to come down here, get a tails first, but then get 2 heads, right? So I'll say whoops, what did I just do? That's not what I wanted to do. You stay there. Okay. So probability of tails and then 2 heads. Well, that would also be 1/8. And there's no other way to do it, right? The rest of these paths have more than, well, either more or less than 2 heads. Like this one's got, let's flip the color here. This one's got 3 heads. If I come this way, I only got 1 head and 2 tails. If I come this way, same thing. You know, and so if I go this way, if I come out to here, I got no heads at all. So we're not interested in any of those paths. So it's one of those 3 paths. They are all mutually exclusive. Those are all the ways that we can get exactly 2 heads. Therefore, the probability of exactly 2 heads is, add them all up, 3/8. 3/8. There we are. So that illustrates what this equally likely stuff is talking about here. Equally likely is going to mean just go ahead and add up your probabilities. Now, I want to, while I'm still here, before I get to the general case, while I'm still here, how can we do this without a tree? So I'm going to say PS. How might we do this without the whole tree thing? Well, you could do it this way. You could say, well, I need exactly 2 heads. So maybe I go heads, heads, and then tails. I have to flip 3 coins. So there has to be 1, 2, 3 coins here. But I want only 2 of them to be heads. Now the probability of doing this and this and this, remember? We've done this very, very recently. You say, well, it's a 1/2 to get the first heads. And then it's a 1/2 to get the next heads. And then to get the tails is also a 1/2. And you want to do all 3 things in a row. And guess what? That comes out to 1/8. And then you would say, well, that's not the only way I could do it. I could do heads, tails, and then heads, right? So you'd have to do a little bit of work to figure out what are all the ways I can get exactly 2 heads. But it's not really that much work in this case. So again, it's a 1/2 to get heads, and then it's a 1/2 to get tails, and then it's a 1/2 to get heads, so that's 1/8. And there's only one other way you could do it, and that's if you get the tails first, and then the 2 heads. 1/2 times 1/2 times 1/2 is 1/8. And since those are all the possibilities, you add, and because they're mutually exclusive, you've listed all the ways to get 2 heads. They're all mutually exclusive. You can just add their probabilities and say, hey, the probability of getting exactly 2 heads is 3/8, which of course is what we expected. Cool. So if you have mutually exclusive events, it's really not going to be that involved to find the probability of A or B. What happened here? This is supposed to be on page 2. Something happened here. Oh, well. So page 2. Hopefully your page 2 looks like this. The general case is Bayes' theorem. The general case means not mutually exclusive events. So let's just write this here, i.e. not mutually exclusive events. So I got a deck of cards here as an example. Let's go back to blue. So there's our standard deck of 52 plan cards. And what we're going to do is we're going to draw one card at random. Just one. Okay, draw a card at random. And let's answer 3 questions. Question A, what's the probability that we get hearts? Well, we can work that out directly. Count all the hearts. There's hearts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 hearts in there, right? Out of a deck of 52. So it's 13 out of 52. Now, it's nice to reduce, but in the middle of the problem, I'm not going to. We'll just leave that there for now. What's the probability of a face card? Well, again, we can do this directly. We just come up to our deck of cards here, and we grab all the face cards, which are all of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. There's 12 of them things. And so that's 12 out of 52. Cool. We're boogieing right along here. Part C. What's the probability that's a hearts or a face? You pick a card, one card. You want to know what's the probability that's a heart or a face. Well, notice something here. Being a heart or being a face card, not mutually exclusive. These are not mutually exclusive events because it's possible to be a heart and a face card at the same time. You could be the Jack of Hearts and now you're both, right? So they're not mutually exclusive, exclamation points. So you cannot just add and say 13 out of 52 plus 12 out of 52 equals 25 out of 52. Oops. That's not a 52. Come on, you. What now? Stop. Okay, out of 52. No, sir. No. You're not going to, you can't. Why? Again, not mutually exclusive. It doesn't work to add. So let's see. Do you see the problem here? Let's look back at our deck of cards. What's the problem with that? Well, when we figured out the probability of hearts, we counted these 13 cards right there, right? And then when we counted the face cards, we counted all of these, all of these, all of these, all of these. Okay, so now I think you see the problem. The problem is we counted those cards twice. You're supposed to count every card once when you're figuring out these probability ratios, not twice. But we counted that one twice because we counted them as hearts and then we counted them as face cards. That's the problem. So here's how Bayes' theorem fixes this. How much room have I got? I better go to here. Bayes' theorem goes like this. The probability of A or B happening is you take the probability that A happens, you take the probability that B happens, you do add them up, but then you subtract the probability of A and B happening at the same time. That is your Bayes' theorem, and this is generally true. And so now we can fix our thing. The probability of hearts, right there, we could put that right there, plus the probability of face, we could put that right there. But then we have to subtract the probability of a heart and a face, which you can count. There's 3 of those, right? It's a Jack heart, Queen heart, King heart. Those are all hearts and faces. There's 3 of those. So it's a 3 in 52 of getting one of those. And if you add that up, 13 plus 12 is 25. Take away 3 is a 22 out of 52. Which if you reduce, it'd be an 11 out of 26, which would be something like a 0.423077, something like a 42.3%. I like to reduce my fractions. In fact, you must. I like to do 6 decimal places minimum. And then, usually for the percent, I let myself start rounding back off and say, well, I don't want to say 42.3077%. That'd be crazy. So I'll just say 42.3%. But having a lot of decimals is usually going to be a good practice. But anyway, That's how you fix it. That's how you fix it. You have to subtract off the overlap. So maybe let's get a new color here, dark purple. So I'm going to say this accounts for the overlap, shall we say. If you just, the probability of hearts is going to count all of the heart cards. The probability of face is going to count all of the face cards. But if there's such a thing as a face card in hearts, then there's some cards you've counted twice. So you have to subtract that off. How many did you count twice, basically? And so, yeah, cool. Bayes theorem. Now, I'm going to throw a little note in here, and boy, I wish I had more space. So I'll just throw it in down here in like a little bubble. So I'll say PS, note. If A and B were mutually exclusive, i.e. no overlap between the two, then this P of A and B would be 0, because there's no such thing as being both an A and a B, because they don't overlap. They're mutually exclusive. And if this is 0, notice it just, the formula simplifies back to what we were doing on page 1. So I always love that about math. It's so consistent with itself. So, just something to notice. So there's your Bayes theorem. Yay, this is a cool formula. Live it, love it, that kind of stuff. Okay, boy, I really messed up my page breaks, didn't I? Oh well. Example 4, another example just to do a few more. We got what now? Certain parking lot contains 4 kinds of cars. We got 50 blue Fords, we got 20 red Fords, we got 70 blue Chevys, we got 10 red Chevys. Okay, cool. So that's 4 kinds of cars. One car is selected at random, maybe to get hit by a meteor or something. I don't know. Someone's going to buy a car. You're just going to buy one at random. Yeah, that's it. Find the probability that it's either a blue or a Ford. And we're going to do it 2 different ways. I'm going to do it by direct counting. Let's do that first. And then we'll do the Bayes theorem next. So direct counting. Sometimes direct counting really is kind of the nice way to go because, well, you can see exactly what's happening. I'm supposed to do what now? Blue or Ford? That would be the number of cars that are blue or Ford. And that would be divided by the total number of cars that you might get, right? So let's see now here. Blue or Ford? Well, those are blue. And those are blue, so add those up. But then also add these because they're Fords. Okay, cool. You wouldn't add those because they're not blue and they're not Fords, so don't add those. Okay, and then divide by the total, which of course includes the 50 and the 70 and the 20, and it would of course include the 10. 10 is part of everything. So there's our ratio. What do we got here? We got 50 plus 70 is 120, plus 20 is that's a 140 on top. And when you add the 10, you got a 150 on the bottom, and yeah, reduce. So 14 out of 15 would be the chance of getting something that's either blue or a Ford. That would be direct counting. And if you have a table like this, there's no reason not to, really. But for Bayes' theorem, just to illustrate its use, we would go like this. We would write it out. The probability of being blue or Ford is the probability of being blue plus the probability of being a Ford, and then minus the probability of being both, which basically means a blue Ford. Subtract off the probability of being a blue Ford. So let's stuff these numbers in here. Maybe I'll change colors for that. So the probability of blue is, come back to our table. You got 120 blue ones out of the 150 total cars, right? This number is still the same. So 150 total cars. How many Fords we got? Well, you would circle like that. There's 70 Fords. So the chance of getting a Ford is 70 out of 150. But then you would want to subtract off the blue Fords. The probability of a blue Ford, which means the probability of one of those, which would be 50 out of 150. Notice what you get is 120 plus 70 is 190, minus 50 is, guess what, 140 out of 150, which is 14 out of 15, which is what we got before. Life is good. So there's the Bayes theorem. You can do some of these problems by direct counting as well. Nothing wrong with that, really. Example 5 is kind of an interesting little one. Everybody likes cats or dogs, right? Everybody is either a cat person or a dog person. That's the claim anyway. Now, the probability of someone liking cats is 40%. The probability of someone liking dogs is 80%. So what's the probability of someone liking both? Okay. There's no direct counting here. Well, maybe I could figure it out, but let's just write down the Bayes Theorem again. The probability that you like cats or dogs. You would take the probability that this randomly selected person likes cats, you would add the probability that this randomly selected person likes dogs, and then you would subtract the probability that this randomly selected person likes both. Now, what numbers did they give us? The probability of someone liking cats is 40%. Put that right there. Right there. Okay. Probability of someone liking dogs is 80%. Put that right there. What is the probability of someone liking both? So they're not telling us this one. So how are we supposed to figure it out? Well, it's because they did, even if it doesn't look like it, they did tell us everybody likes a cat or a dog, which means the probability of someone liking a cat or a dog is 100%. Get it? In this particular case, everyone likes either a cat or a dog. Now, if that's true, everyone likes either a cat or a dog, or maybe both. If 40% like cats, let's go back to this color. 40% like cats, 80% like dogs, and it's supposed to add up to 100%. Notice right now we're adding up to 120%. That's too high. So that means we must have to subtract off 20%. You could solve it algebraically, of course, if you wanted to, but you can kind of see that. It has to add to 100%. 40 plus 80 is 120, so I must have to subtract off 20%. Isn't that something? I don't know if I believe that, but whatever. According to this data, that would be the case. So just one more example? I think so. Let me check. Of course, the page break is messed up. Ugh, I hate that. Anyway, Veronica's cooler contains 20 Cokes and 14 Pepsis. Okay, this problem is going to not just be a Bayes theorem. It's going to be like more than one thing going on. We can review some of our older things that we've seen before. Let's see if we know how to do all this. If we remember, Veronica's cooler contains 20 Cokes and 14 Pepsis. We're going to select 2 at random. What's the probability both are Cokes? Well, that's kind of like saying I want to draw 2 things. I want the first one to be a Coke. I want the second one to be a Coke. Remember how we did this? We would say, well, we're doing 2 things in a row. That's multiplication rule. The 2 things we got to do is, first, we have to draw a Coke. So the first one's a Coke. And then we have to draw a Coke again. The second one has to be a Coke. Now the thing is, there's we're drawing without replacement, so there's going to be sort of a dependence. The probability of getting a Coke second is going to depend on whether you got a Coke first. Because if you did get a Coke first, you removed one. It's going to be harder to get another one. So let's see here. The probability of the first one is a Coke. Okay, there's 20 Cokes out of 20 plus 14 is 34 cans. Now, you just got a Coke. One of them is missing. There's only 19 Cokes left. And by the way, there's only 33 Cokes left. 33 cans left. I'm sorry, cans left. Remember this thing? We've seen this before. So what is this? This comes out to, I got 190 over 561 after my calculator reduced for me. So that would be, as a decimal, approximately 0.338681. So something like 33.9%. Pretty good chance, actually. Find the probability both are Pepsis. Both are Pepsis, that's kind of the same thing. The probability that I go a Pepsi 1 and then a Pepsi second. Well, first you got to get a Pepsi first. And then Pepsi second, given that the first one was a Pepsi. So getting a Pepsi first. There's 14 in there out of 34 cans. And then if you grab a Pepsi, there's only 13 left. And now there's only 33 cans left. And I got a 91 out of 561. And that's approximately equal to a 0.162210. So this is like a 34% almost. This is like a 16%. A little less than half is likely to get 2 Pepsis as to get 2 Cokes. Cool. So you remember doing this? These are called conditional probabilities, you might recall. What are called conditional probabilities? These things. The probability that you got a Coke second, given that, on the condition that you got a Coke first. Probability. I always have a hard time with this word. Probabilities. There's so many words, so many letters in there. Anyway, these are called conditional probabilities. Now, let's go to part C. It says find the probability both are the same. Either both are the same means either both Coke or both Pepsi, right? Well, we figured out the probability of both Coke, and we also figured out the probability of both Pepsi. Can we simply add those? Well, we can if these are mutually exclusive events. Now, you got to admit they are. Getting 2 Cokes and getting 2 Pepsis, you're not going to do that at the same time. Not if you're only drawing 2 cans, you're not. So if they're mutually exclusive. Mutually exclusive. So add those 2 things up and you get, well, let's be explicit about it. Take the 0.338681, add the 0.162210, you get 0.500891. So just about 50%, right? Just a touch over 50%. Question D. What's the probability of getting one of each? Think about this one. This was a topic of a recent homework. The probability of one each. Well, you kind of, sometimes if you think about taking a direct approach and you start to get bogged down, that's a hint that you should do something else. So you say one of each, huh? So maybe I get a Coke and then a Pepsi. Maybe I get a Pepsi and then a Coke. Well, actually, this problem might not be so bad to do directly. But we don't have to do it directly because, here you would just do the probability that the first one is a Coke times the probability that the second one is a Pepsi, given that the first one is a Coke. We could do that. Actually, I'm going to do that. Watch me do that. The probability that the first is a Coke is what now? There's how many Cokes? There's 20 out of 34. And the probability that the second one's a Pepsi, knowing that the first one's a Coke. Well, see, you'd still have 14 Pepsis because you took a Coke. You'd only have 33 cans left. So, yeah, let's work this out. Where's my Tuckle typelator? Here it is. Come on, you. So, let's see. I go 20 divided by 34 times 14 divided by 33 equals, boom. And this is saying 140 out of 561. And I'll leave it as a fraction for now. Here you do the probability that you got a Pepsi first and the probability that you got a Coke second, given that you got a Pepsi first. And guess what? At first you have 14 Pepsis out of 34 cans. Next you have, you still have 20 Cokes left out of 33 cans. And guess what? This is coming out exactly the same thing. Now those are both ways of getting one of each. They are mutually exclusive. You can't get a Coke and then a Pepsi and at the same time get a Pepsi and then a Coke, right? Mutually exclusive. I'll just use ME. So add, and you would get, I guess, 280 out of 561. And let me make a decimal out of that. 280 divided by 561 is, come on you, 0.499109. And now I want you to notice something here. Not that. This. Notice this. Probability of one each. I had in mind the complement rule. Oh, I see what's making all this noise. My thing's moving. Complement rule. Not one of each is both the same, right? If they're not one of each, they must both be the same. This is the probability that we worked out earlier that they're both the same. So we don't want that. So we go 1 minus 0.500891. And guess what? You get exactly the same thing. 0.499109, exactly the same thing. So there's 2 good approaches to take to this one. I like the complement rule better because it's faster. But we could have done that one directly, it turns out. Sometimes you can't. If you're drawing 5 cans or something, you probably don't want to do it the direct way. All right, and it looks like there's one more part here. Let's go back in time. All right, get in the Wayback Machine, go back in time, and before any cans are removed, we add some stuff. We add 10 Coke Zeros, which is basically a better version of Diet Coke, and 12 Diet Pepsis. We add those to the mix. And then we're going to select a can at random, and yeah. First, let's figure out what we got here. So we started with, let me remind myself, 20 Cokes, 14 Pepsis. Okay, we start with 20 Cokes, 14 Pepsis, except now we're adding some more to the cooler. 10, I'll put CZ for Coke Zero, and 12, I'll put DP for Diet Pepsis. Okay, that's our new cooler. And by the way, how many cans we got now? 20, 34, 44, 54, 56 total cans. Okay, cool. So now let's get to the actual question here. I added my Cokes, I added my Diet Pepsis, my Coke Zeros. Yep. One can selected at random. Cool. Probability is either some kind of Coke, some kind of diet. Okay, so both the Coke Zero and the Diet Pepsi count as some kind of diet, right? Both the Coke and the Coke Zero count as some kind of Coke. Okay, here we go. We're going to do it now. The probability of, what's it say? Coke or diet. Bayes Theorem. You take the probability of the Coke, you'd add the probability of a diet, you'd subtract the probability of a Diet Coke, basically. It's both diet and Coke. Now the probability of a Coke is, you look at this number, 20 out of, well, wait a minute, you wouldn't look at that number. It doesn't say Coke only, it says, some kind of Coke. These are also Cokes, actually. So that would be a 30 out of 56, and then the probability of some kind of diet, I should probably say it that way, some kind of diet, 10 plus 12. 22 of those out of 56 cans. And then the Diet Cokes, otherwise known as Coke Zeros, there's only 10 of those. That's our overlap that we need to subtract, right? So if you look at it this way, I added up some Cokes to get this number. Then I added up some diets to get this number, but then I counted those twice, and that's why I'm subtracting it off. So if we work it this way, what am I getting here? I'm getting 30 plus 22 is 52, minus 10 is 42 out of 56. And by the way, that's what you would get if you just added directly. 20 plus 10 is 30, plus 12 is 42, right? 42 out of 56 would be our answer. That would be reducing to 21 out of 28, which is actually exactly 3/4. I should put 3/4. 0.750, 75.0%, whatever. Cool. Okay, so I think that's the end of the lecture, right? Yep, dots. Dots are the end. So I hope you like this. A or B? Well, there's this, I guess the main point you want to keep in mind is that sometimes, if you want the probability of A or B, sometimes you can just add the two probabilities up. But you got to be careful. You can only add the two probabilities up in the case of mutually exclusive events. If they're mutually exclusive, you can add them up. You have to keep in mind that sometimes events are not mutually exclusive and there's some kind of an overlap going on, in which case you should not just add them up because there's going to be this correction factor. That's the main thing. That's the main takeaway from this lecture, I believe. Yeah. Who turned off my computer?